initially 0.3 moles of H2 and or hydrogen gas plus 0.3 moles of iodine gas is injected into the closed container of volume 2 cubic decimeters. Equilibrium is established at 448. The equilibrium constant for the reaction at 448 is 50.5. Now, this is the first thing to note. This question is talking about injecting things, it's giving you the volume, and it's giving you initially. These are all the keywords that we've seen in previous questions. However, in this particular question, they don't ask you for the equilibrium constant. Rather, the question says calculate the number of moles of hydrogen iodide produced at equilibrium. Now, you got to be very careful here because they're actually asking you for your value inside the table and they're giving you the end result. So there's going to be some form of back substitution or working backwards. That's what this question requires. Now, a lot of students, because they only learn the table for the first 3 examples and they leave this trickier one, they often get this question wrong because of the algebra involved. It's not a difficult question, it just requires some backward integration or some working back. Okay, I'm going to give you the reaction because that's usually given to you. This reaction is H2 plus, okay, let's just put some space in between, plus I2 gives me HI, and 2 of it, 2HI, and everything is in the gaseous phase, so they're all relevant to the table that we want to construct. So let's just draw that table down like that. Let's just get a black thing going over there. And if you've noticed, I'm being a bit smarter about this time. I'm actually drawing the table with a block. And then we will construct our lines below that like such and like such. And then we'll have the first row, which will be initial. The second row will be reacted / produced. The third row will be that, and then over here we will calculate the equilibrium constant. Equilibrium concentration. So you have initial, you have reacted / produced, you have the equilibrium number of moles, and then finally you get the equilibrium concentration, right? And as you know, that's just equal to N divided by V. So I've got a little bit more space there in order to calculate that. Okay, so then remember reacted / produced, you need to put in your stars. That indicates that this entire row going across must be proportionate with the other members of that row. And yeah, now we can start throwing in these things. Okay, I'm going to write down Kc's formula on this side, because it would become relevant. Kc is equal to the concentration of hydrogen iodide raised to the power of 2 divided by hydrogen gas multiplied by iodine gas. Right. Okay. Okay. So that formula is going to become relevant. And what they really want is not the concentration at equilibrium, but they want the value of the number of moles at equilibrium. So we're going to have to fill in this table, and this is the first example because often people say it involves an X or something like that. This is that question. You're going to have to introduce a variable and you're going to have to work backwards, and that's when they give you the value of Kc, right? And you have to calculate something that's actually written in the table. So 0.3 moles of iodine gas, so let's just put that in there, 0.3, and 0.3 moles of, sorry, that was hydrogen gas, this is the iodine gas. They both were 0.3 moles, and they were injected into a container of volume of 2. We didn't start with any of the hydrogen iodide, so that's going to be 0. Okay. Right. Now, because we're not starting with anything, we have to produce on this side, and therefore, this is going to be a plus, this is going to be minus, this is going to be minus. Usually, you would inspect the change. In this case, you're inspecting that you're starting with nothing, you have to therefore produce something. Okay. Now let's look at the mole ratio. The mole ratio says that this is 1:1, 1. Okay, let's just write it in here. 1:1 is to this 2 over here. So I'm going to write over that 2. Okay, 1:1:2. Whatever is here must also be here, and whatever is here must be doubled to get what's going to be over there. That's how the mole ratio works. That's why we have our stars. Okay. So what we are now going to introduce is a variable to make all these things easier. I'm going to say that I'm going to call the variable x, and this is where we really start with our calculations. Okay. This variable on this side is also x, because 1 is to 1. And then on this side, whatever I have here, I need to double it to get to this side. So that's going to be 2x. Okay. Now you simply tell me, what must this row going across here be? That's 0 plus 2x, which is just 2x. That's 0.3 minus x, which is just 0.3 minus x. And this over here is also just 0.3 minus x, right? So very, very simple. Okay. And as you know, to get this thing on this side, I need to take 0.3 minus x, and I need to divide it by the volume in cubic decimeters. In this case, it's going to be divided by 2. So this is 0.3 minus x all over 2. And on this side over here, and I understand why I'm writing skews, because the table is entirely skew. I didn't even know that. And this one over here is going to be 2x divided by 2. Right, and that one's fairly trivial, because 2x divided by 2 is just going to be x. So let's put that in on this side. I'm going to cancel out that in a different color. Now based on this, you can see there's only one variable in this entire thing, and I've only got one equation. So one variable, one equation, completely solvable, and let's do that now. You were given the value of Kc, so we substitute that in directly, and I'm going to say in the place of Kc I've got 50.5 is equal to the concentration of hydrogen iodide at equilibrium, which is going to be just x, and that's going to be squared, divided by this thing multiplied by this thing. But they are identical, and because they are identical, I'm going to write it out the long way for you for now. 0.3 minus x all over 2 multiplied by 0.3 minus x all over 2. Okay, and this thing over here, this is just the top thing, which is x squared, divided by that thing, which is going to be 0.3 minus x all over 2 all squared, right? So the moment I have the top and the bottom squared, that's a trivial situation in which you can see the entire thing is squared, and this is really maths, it's not physics right now. And how can I get rid of those squares? Well, I could simply just take the square root of both sides. Okay, so I'm going to square root this thing, and I'm going to square root that thing, right? And when I square that thing, the square here falls away and the square there falls away. And that gives me the following solution. That's going to be 7,11. And this thing is going to be x divided by 0.3 minus x all over 2. Okay, and at this point in time, the rest of this is just going to be algebra. You will come out to find the value of x, and with a little bit of algebraic manipulation, I don't have the space to do so, you should get, therefore, x will equal to, I'm just going to continue on this side, x equals 0.23. Now that's the value of x, but they want the value of hydrogen iodide at equilibrium. So we go to the equilibrium column, and we see hydrogen iodide is going to be 2 multiplied by the value of x. So therefore, number of moles, the number of moles of Hi at equilibrium is equal to 2 multiplied by 0.23, which is going to be 0.46. Okay. So I'm sorry about the colors there, but that will be the correct version, 0.46. And again, it's the number of moles, so 0.46 moles, right? So this was a trickier question. You weren't asked to calculate Kc, but you were asked to work backward, and you have to find something that's in the table. It's fairly trivial, it's fairly simple. You get this on the basis of recognizing that the equilibrium constant was given. They gave you the result, and therefore you had to work backwards. So good luck, people.